On July 1st, astronomers working with the Asteroid Terrestrial Impact Last Alert System, ATLAS, detected an unusual object racing through the solar system on a trajectory that suggested it was not gravitationally bound to the Sun's. Subsequent observations quickly confirmed that this object, now designated 3I/Atlas, was an interstellar visitor, only the third such object ever detected passing through our solar system, following the discoveries of 1I/Oumuamua in 2017 and 2I/Borisov in 2019. The arrival of 3I/Atlas immediately sparked intense scientific interest, as these rare visitors offer a unique opportunity to study material formed around other stars and preserved for billions of years in the cold depths of interstellar space. As astronomers continued to monitor 3I/Atlas, they found that it displayed a number of unusual and intriguing characteristics. Among the most striking was the presence of what appeared to be an anti-tail, a feature that pointed toward the Sun rather than away from it. This observation was made during July and August, when the object was still far from its closest approach to the Sun. Such a phenomenon is rare, especially in interstellar objects, and it prompted a range of interpretations and debates within the astronomical community. To understand why this feature attracted so much attention, it is useful to review how comets normally behave. Comets are composed largely of ice, dust, and rocky material. As they approach the Sun, solar heating causes the volatile ices within the nucleus to sublimate, transforming directly from solid to gas. This gas carries dust particles with it, forming a surrounding cloud known as the coma. Radiation pressure from sunlight and the flow of charged particles in the solar wind then push this material away from the Sun, creating the familiar cometary tail that extends in the opposite direction. In many cases, comets exhibit two distinct tails, a dust tail, which is curved and influenced by the comet's orbit, and an ion tail, which is straighter and more directly shaped by the solar wind. Occasionally, however, observers notice what appears to be a tail pointing toward the Sun. This feature is commonly referred to as an anti-tail. In most cases, anti-tails are not truly directed sunward, but are instead optical illusions caused by the geometry of the comet's orbit and the observer's viewing angle from Earth. The European Space Agency has explained that when Earth lies within or near the plane of a comet's orbit, the wide dust tail can appear to fan out in such a way that part of it seems to extend toward the Sun. In reality, the material is still moving away from the Sun, but perspective effects make it appear otherwise. True anti-tails, however, are far rarer. These involve material that genuinely appears to be located sunward of the nucleus, often consisting of larger dust grains that are less affected by radiation pressure. In the case of 3I/Atlas, researchers from Harvard University, including Avi Loeb and Eric Quito, published a preprint paper describing observations that suggested the anti-tail they detected was not simply an illusion of perspective. They noted that observations made when the object was approximately 3.8 astronomical units from the Sun showed an elongated coma resembling a tail, but clearly pointing in the Sun's direction. According to their analysis, this type of anti-tail may not have been previously observed in quite this form, particularly for an interstellar object. Loeb, known for his willingness to explore unconventional hypotheses, commented that if the object were an alien spacecraft slowing down using thrust, the observed transition from an anti-tail to a normal tail near perihelion could be expected. While this suggestion drew public attention, many astronomers emphasized that extraordinary claims require extraordinary evidence, and that natural explanations must be thoroughly examined before entertaining more speculative ideas. Indeed, other researchers quickly pointed out that similar features have been documented in the past. Jason Wright, a professor of astronomy and astrophysics at Penn State University, noted that anti-tails have been observed before, with examples dating back at least to Comet Kohoutek in 1974. These historical observations demonstrate that while anti-tails are uncommon, they are not unprecedented and can arise from well-understood physical processes. Further clarification came from astronomers studying the behavior of dust and gas ejection from rotating comet nuclei. Michael Bush, an NSF Astronomy and Astrophysics postdoctoral fellow, explained that material expelled from localized active regions on a rotating nucleus can be ejected either ahead of or behind the comet along its orbital path. Once released, smaller particles are quickly pushed away by radiation pressure and the solar wind, while larger grains are less affected and can spread out along the orbit itself. Over time, this process can lead to dust both in front of and behind the nucleus, creating features that may resemble an anti-tail when viewed from certain angles. In solar system comets, this mechanism eventually produces meteoroid streams that trace the comet's orbit and can give rise to meteor showers when Earth passes through them. Although the existence of a natural explanation reduces the need for exotic interpretations, the presence of an anti-tail in 3I/Atlas remains scientifically valuable. Interstellar comets are fundamentally different from comets formed in our own solar system. They originated around other stars, likely in environments with different chemical compositions, radiation fields, and formation histories. As such, their physical and chemical properties can provide insights into the diversity of planetary systems throughout the galaxy. Another remarkable aspect of 3I/Atlas is its potential age. Some researchers suggest that it could be up to 10 billion years old, meaning it formed during an earlier epoch of the universe, possibly before the Sun itself existed. If true, this would make the object a pristine time capsule, preserving information about the conditions in its parent system long before our solar system formed. For most of its existence, the comet would have drifted through interstellar space at extremely low temperatures, likely below 10 Kelvin, which would have preserved volatile compounds that are rarely seen in solar system comets that have undergone repeated heating. This context makes observations of 3I/Atlas as it approaches the Sun particularly important. According to the authors of another recent, yet-to-be peer-reviewed paper, it is statistically unlikely that 3I/Atlas has passed closer to any star than it will pass to the Sun in 2025, at least since its ejection from its original protoplanetary disk. This means that the current encounter represents the most intense heating event the object has experienced in billions of years. Observing how its activity develops as it warms provides a rare opportunity to study how pristine interstellar material responds to stellar radiation for the first time. Before the object moved out of favorable viewing geometry from Earth, astronomers were able to track its evolution over several months. These observations revealed that the anti-tail seen earlier in the year gradually transformed into a more conventional tail by September. This change is consistent with increasing solar heating and the growing influence of radiation pressure as the comet moved closer to the Sun. The transition supports the idea that the earlier anti-tail was related to the distribution of larger dust grains along the orbit rather than any unusual propulsion mechanism. Even though 3I/Atlas eventually moved out of Earth-based view, it could not entirely escape scrutiny. Instruments aboard spacecraft orbiting Mars continued to observe the region of space through which it passed, providing additional data that may help refine models of its behavior. Combined with earlier observations, these datasets will allow astronomers to better constrain the object size, composition, rotation, and activity levels. In the broader context of astronomy, the discovery and study of 3I/Atlas highlight how much remains unknown about interstellar objects. Each new detection challenges existing models and forces scientists to refine their understanding of cometary physics, planetary system formation, and the processes that eject material into interstellar space. While speculative ideas can capture public imagination, the true value of objects like 3I/Atlas lies in the careful accumulation and interpretation of data, grounded in known physical laws. Ultimately, 3I/Atlas serves as a reminder that the solar system is not an isolated island, but part of a dynamic galaxy filled with wandering debris from countless other stars. As detection technologies improve and survey systems become more sensitive, astronomers expect to discover many more interstellar visitors in the coming decades. Each one will bring new clues about the environments beyond our solar system and help place our own planetary neighborhood in a much larger cosmic context.